Hello everyone, welcome from our algorithm mini project, which is about the reference search algorithm. We can also call it the Pathfinder algorithm. So let's get started. So these are our team members, Matthew, Jim, Sam, and P. So the Pathfinder, and these are our former names, and then started. Let's start with a conceptual overview. So before talking about anything else, we have to know what is a graph. Because our preferred search algorithm is highly connected with that graph. So what is a graph? A graph, a graph consists of nodes. You can see here, this 0, 1, 2, 3, 4. Those are the nodes. We can also call them like vertices. They are the same. And we have nodes, and we have connections, which are called edges. So the connections between each node, the edges, and consisting of them, like combine them, this is a graph. So this is a graph, and there are different types of graphs. One is a derived graph. Derived graph, where the edges have a direction, and underived graphs, where the edges, the connection doesn't have a direction. Weighted graph, where edges have a values or weights. Also, and unweighted graphs, where the edges doesn't have values. So it is like roads and towns or roads. You can see them as roads between each town or where there is direction, or roads where you can go like there is no direction. You can go either way, or you can view like weighted and unweighted graphs as the paths between the mountains and the plains. So for the mountain, like going from one place to another, it is easier, but uh, it's not the same. It's not easier. I mean, it is gonna be harder and easier or something like that, but it is gonna be the same for the unweighted graphs, which means like on the planes. So those are the types of graphs, and you can see here. So those are the weighted graphs and weighted graphs and dried graphs, etc. Many types of graphs. So let's get started. Let's talk about what is the breadth first search algorithm. The breadth first search algorithm, BFS, it is an algorithm which explores all neighbors nodes level by level. You start with a node first, and you examine like the neighboring nodes, and let's get started. Instead the root node and visit each neighbor node before moving to the next levels. Breadth search algorithm use a queue for its exploration. As an example, you can see here, it starts with the source node, the root node, 0. From 0, it goes to 1 because it is the nearest layer to the 0. And after 1, you will not go to 4, you will not go to 5, you will go to 2 because 2 is the closest to the 0 after 1, and then go to 3. So the 3 closest to 0 are now search, which means added to the queue, and it will go to 4 because 4 is the closest to the 1, and then 5, and then 6 to the 2, and then 7 to the 3 on 2. So 0, 1, 2, 3, 4, 5, 6, 7. This is the order of the breadth algorithm who's gonna who's gonna search. Now you get the idea of the breadth search algorithm. So let's study why is breadth search algorithm used. So the breadth search algorithm is used to find the shortest path in unweighted graphs, and it's gonna be used in network exploration, finding connections. It's also gonna be used in NPC pathfinding in AI in games, like NPC and player characters, and also about finding the degrees of separation in social networks. Those are the three that we're gonna use breadth search algorithms. So let's study step-by-step process of breadth search algorithm. It starts with a root node. As I mentioned, it is initial node, source node, same. Add the root node to the queue, which means that it is searched already. Visit each neighbor of the root, and mark visited nodes to avoid cycles, which means add it to the queue. Repeat for all neighbors levels by levels until all are gone. Okay. Example is start from node A and the nearest are B and C, and move to B's neighbor. After visiting all B's neighbor, move to the C's neighbor, and so on, and so on, and so on. So let's see the time complexity. The reverse visits all nodes and edges, so the time complexity is O of V plus E. V is number of vertices, E is number of edges. This is the reverse algorithm time complexity. And this is the time complexity breakdown. Q operations take all of one time. Each node is NQ and DQ exactly once. Neighborhood checking happen once per edge. So, and then we're gonna compare breadth first algorithm and the depth first algorithm in time space complexity. Okay, depth first algorithm, which is DFS, is different, a little bit different from breadth first algorithm. We're not gonna talk about detail in here because this is focused on the breadth first algorithm only. So let's only compare the time space complexity. The time complexity is same, is O of V plus E, but the space complexity different for the queue and for the recursion step. So this is for the conceptual overview of Professor algorithm, and my friend will tell about the application of the breadth search algorithm here from now. Thank you so much.
Now let's talk about the time complexity of the breadth-first search algorithm. The BFS algorithm explores every node and edge exactly once in the worst case, and its time complexity is given by O of V plus E, where V is the number of vertices or nodes in the graph, and then E is the number of edges or connections between the nodes. This means that the time it takes for the BFS algorithm to complete is directly proportional to the number of nodes and the number of connections between them. And so the larger the graph, the longer the algorithm will take to explore it. To break it down a bit further, let's analyze the time complexity in more detail. So the operations of enqueuing and dequeuing a node from the queue takes O of one time each. And since each node is enqueued and dequeued exactly once, this contributes O of V to the total time complexity. For each node, BFS algorithm checks all of its neighbors, and since each edge is explored only once when the node is either enqueued or dequeued, this contributes O of E to the total time. So the total time complexity for the BFS algorithm becomes O of V plus E, like I mentioned in the beginning. And so combining both the time for visiting nodes and edges. Lastly, let's quickly compare the BFS algorithm to the DFS algorithm in terms of time and space complexity. Both BFS and DFS algorithms have the same time complexity of O of V plus E, as both explore every node and edge once. However, the space complexity is where they differ, since BFS uses a queue, and in the worst case, it can store all V nodes, while on the other hand, the DFS algorithm uses recursion, and its space complexity is also OV because it keeps tracks of nodes in the recursion stack. So while their time complexity is identical, the way they store nodes during traversal is a little different.
Applications of Breadth-First Breadth-First or BFS is widely used in graph traversal. It efficiently explores all neighboring nodes before moving deeper into the graph. This characteristic makes BFS particularly useful for solving problems related to the shortest paths, such as finding the quickest route in a network. Additionally, it helps analyze connectivity by determining whether two nodes are connected and identifying all reachable nodes from a given starting point. BFS is particularly effective in finding the shortest path in unweighted graphs. The algorithm explores each level of the graph systematically, ensuring that every step takes you one level deeper. And there are some key applications of this capability, and they are network routing. BFS helps in determining the optimal paths for data packets traveling through networks, ensuring efficient communication. GPS navigation systems. It is used in GPS applications to calculate the shortest route between locations, allowing users to navigate efficiently. And BFS plays a significant role in exploring connections within social networks. By traversing through users and their relationships, BFS can uncover valuable insights such as friend suggestions. It analyzes the network to recommend potential friends based on mutual connections, enhancing user engagement. Degrees of separation. BFS can determine the shortest path between users, revealing how closely connected they are within the network. For instance, for example, platforms like LinkedIn and Facebook utilize BFS to enhance their social connectivity features, making it easier for users to discover new connections and strengthen their networks. BFS is a fundamental technique used by web crawlers to explore web pages effectively. The, the process begins at a specific web page, and BFS systematically explores all reachable links, allowing it to gather data from a wide array of sites. This approach is particularly efficient for broad exploration as it ensures that all links at the current tab are visited before moving on to links at the next level. This capability is essential for indexing the vast information available on the internet and helps search engines deliver relevant results to users. BFS is also widely used in game solving algorithms, where it assists in finding the shortest path in maze or puzzles. This method is particularly effective in scenarios where the goal is to navigate complex structures such as solving Rubik's Cube. BFS can explore all possible moves to determine the quickest solution. 2D grid games. It efficiently finds the shortest path to reach a target while avoiding obstacles. BFS in robotics. Robots utilize BFS to traverse grids and find optimal paths while avoiding obstacles. This application is vital in some contexts, such as self-driving cars. BFS helps these vehicles determine the safest and most efficient routes in complex traffic scenarios. Warehouse robot. It enables robots to navigate aisles and shelves effectively, optimizing their paths for picking and delivering items. Advantages and limitations of BFS. Now let's discuss the advantages of reverse completeness. BFS guarantees finding a solution if one exists. This makes it a reliable choice for exploring such spaces where a solution may not be immediately apparent. Shortest path. In unweighted grabs, BFS always finds the shortest path from the starting node to the target node. This property is crucial in many applications, such as network routing and navigation systems. Simple and intuitive. The algorithm is straightforward and easy to understand. Its systematic level by level exploration of nodes makes it intuitive, making it accessible for both beginners and experienced programmers alike. These advantages highlight why BFS is a popular choice. BFS is a popular choice in various applications across computer science and artificial intelligence. While BFS has its advantages, it also comes with some limitations. Memory usage. BFS requires a large amount of memory, especially when dealing with wide graphs. The need to store all nodes at the current graph can lead to significant memory consumption, which may be impractical for extensive networks. Slow on large graphs. The algorithm can be time-consuming when dealing with large or deep graphs. As it explores all nodes level by level, the number of nodes to process can grow exponentially, leading to increased computation time. Not ideal for weighted graphs. BFS is not suitable for graphs with weighted edges, as it fails to find optimal paths in such scenarios. For weighted graphs, algorithms like Dijkstra's are more appropriate. These limitations should be considered when choosing BFS for specific applications, especially in complex scenarios. When comparing Preferred search (BFS) with default search (DFS), there are key differences to consider. Exploration method: BFS explores nodes level by level, ensuring that all nodes at a given depth are visited before moving deeper. In contrast, DFS dives deep into branches, exploring as far down a path as possible before backtracking. Memory usage and path granting: BFS typically uses more memory because it needs to store all nodes at the current level, but it guarantees finding the shortest path and weighted graphs. On the other hand, DFS is faster and uses less memory as it only needs to keep track of the current path, but it may not find the shortest path. Understanding these differences can help in choosing the right algorithm based on the specific requirement of the problem.
Hello, I'm going to be presenting about what is in our code, and I will be doing the demonstration of our game throughout while I'm explaining about this code. Okay. Okay, so first, let's start with the pseudocode of our breadth search algorithm. Okay, so this is the pseudocode, and I will be explaining the pseudocode while I am showing you the flowchart of the code. Okay, so in breadth search, and we call it like BFS, we start by initializing a queue with the starting node and marking it as visited. Okay, so when the queue is not empty, we dequeue the front code and visit its unvisited neighbors. For each unvisited neighbor, we enqueue it and mark as a visited. This process continue until the queue is empty, ensuring that each node is visited level by level from the starting point. By this way, it just loop around all the nodes and ensuring that all the nodes are visited. Yeah. Okay, so let's explain our code. Okay, so you can see in here, first of all, we use the Pygame to implement our game, and we also import some of the necessary libraries for our codes. Okay, first of all, we do the constants, and we kind of define the grid size, colors, and dimensions, and also we also initialize the Pygame. We're creating the main display window. Okay, so this is just the usual basics. So let's go to the next one. Okay, so in here, I use the custom images for the starting point, obstacles, and the ending points like that. So that's why I need to use the images from my local computer, and that's why this code block is needed and necessary to load them into my Pygame. Okay. Okay, so creating the grid. Okay, so in here we created a 2D grid representing our game area. Each cell in the grid initialized to 0, which means it's walkable, it's not obstacle. So we also initialize the variables from the start node and endpoints and the path that our algorithm will find. Okay, so the next thing is Okay, so this is the most important part, and this is the important part of the BFS like implementation. This is a professor algorithm code. Okay, so to explain this, as I have also mentioned earlier in the pseudocode, so inside the function, like we use like the queue to manage the cells being explored. Okay, I will show you this one to make it like the more visible. This is a game that we implemented, and you can see that we can add the like samples are here. So this is just like the small demo. I will show you more later. Okay, and like we dequeue manage the cell, and we also make a like dictionary to store the parent of for each node and like the pet reconstruction. Okay, so as like BFS like algorithm explore like each node, it checks it also its neighbors. Like if a neighbor is walkable and which is not an obstacle, it is added to the queue. We visualize the BFS explanation by drawing the like visitor node in yellow, as I already showed it, the yellow one, and introducing a delay for like better clarity in the visualization. Usually it's like quite faster than this one, but we added the delay like for the like the demonstration. Yeah. Okay. And the next one is the basic function, the result gain. You can see that we got a reset button here, like because like every time like if we didn't add the reset button, every time we complete this one, we have to close the Pygame window again and open it again. It's very time consuming and it's not functioning well. So we added a restart button, so which can be restarted as we like open from the start again. So this button is really useful, and it's very like its functionality is like very quite useful. Okay, so the next thing is the main loop. Okay, so in the main loop here, what we do here is like pretty much like time consuming, but in the main loop we handle like events and user interaction, like drawing the grids and managing the like gain stakes. Okay, so user can click. Okay, let me show you here. We can click it. This is a starting point, which I represent as a robot, and for the ending point, this is a cube. And okay, so let's say this is an ending point. Okay, like when I click somewhere else, okay, so it will be like the BFS algorithm will be walking, and it will just go through like every node, like until find the shorter packs, like the shorter pack yeah. Okay, so when we like restart it, okay, we just restart it. Okay, and also we have also, let's go to the next one, drawing the start and button point that I've already explained. This one we can draw the like start and button point here, so I will just skip it. Okay, so we have like two button, edit and restart. Okay, so in the edit mode we can add more obstacle here. You can see that you can add any obstacle you want in the cell that is available. So if I click it again, it will remove the obstacle. Okay, so if I'm like okay with this one, okay, let's edit the editing mode. Now it's green again, so let's start the start point and the ending point, and let's find the shorter packs between these. Okay, so the blue the blue cell like represent the shorter packs algorithm that he found while like traveling all the nodes. Okay, so this is for the result part. Okay, let me see, like for the like the first image, it's just the like when we open the game, like we can see this picture, and for the second is the editing mode. We can add or remove the obstacle whatever we want in the available cells. Okay, so the next thing is like you can see the yellow is the visualization of our BFS algorithm, and while it's traveling, like it's like searching for every nodes and the neighbors of each parent nodes. And the last image you can see here like show the shorter packs algorithm with the blues, like with the blue color. Okay, so before I get here, I want to like show the demonstration of our game properly. Okay, so I will just click restart. So in here you can see just a white cell, which means that there are no obstacles or walls. So I will just add more obstacles just randomly. Okay, okay, so I will like close the editing mode, and this is the start point and this is the ending point, and I click it. You know, this is a visualization of the BFS algorithm, the yellow one, and this is the shorter packs, the green one. sorry, the blue one. Okay, so we can just click restart and do it all over again, just like this. Okay, so this is our like demonstration of our game, and let's go to the next part. Thank you.
Now I want to discuss the challenges we face during the implementation of our BFS visualization and some potential optimizations that can be done. So one of the primary challenges was managing the visualization itself. Since when rendering large grids, we noticed a huge delay in updating the grid based on each step of the algorithm. And so as the size of the grid increased, the computer obviously had to work harder, and so we experienced noticeable performance drops, especially in the more complex pathfinding scenarios where many nodes had to be processed at the same time. To address these challenges, we can optimize the BFS algorithm in several ways. First, by minimizing unnecessary grid updates, we can enhance the speed of visualization. We can also leverage more efficient data structures like queues, which can improve the overall performance of the algorithm. Additionally, we might also consider alternative algorithms, such as the A-star search algorithm. The A-star search algorithm utilizes heuristics to guide the search, often resulting in faster and more efficient pathfinding. By tackling these challenges and implementing these optimizations, we can significantly enhance both the performance and user experience of our BFS visualization.